Right, hi guys. This is essentially a trial run to see whether or not this is a useful thing. So if you do find it useful, please let me know in the comments and I can make more of these. If there are specific topics, questions that you'd like me to make something similar to this for, do let me know and I will try my very best to do that, although I can't guarantee the time scale because it is after all the Easter holidays. Right, so this question caught my eye. It's the second half of it that I find interesting, but I'll go through it from the start and I'll try my best to explain what I'm doing. So we've got a single slit, two pictures obtained by varying the slit width only, so the same wavelength used in each of these. Explain whether A or B has the wider slit. What we know about diffraction, if you think about the sort of lambda equals AY over D, A is the aperture, Y is the size of the spread. So as A gets smaller, Y gets bigger. So it's B that has the wider spread and therefore must have the narrower slit. So 2A must have the wider slit. Because it's a narrower spread of diffraction. So, it does say explain. There's two marks for this. I'm assuming that's the first mark. 2A has the wider slit. And for my explanation, all right, that a narrower slit implies a wider spread or greater angle of diffraction. You could probably get that second mark for simply saying 2A has the wider slit because it has a narrower spread or something like that. Okay, what can be done to the single slit to obtain the greatest amount of diffraction? You get the most diffraction when the slit width is roughly equal to a wavelength. So make slit width roughly equal to wavelength. The easiest explanation of why that is really comes from the diffraction equation. If you think of n lambda equals d sine theta, it's always worth remembering that this top one is just an approximation of that bottom one. They're the same equation. The top one is an approximation that holds good for n equals 1. So if we're talking about the width of a central beam, we're left with an equation that looks like this: lambda equals d sine theta. This is an approximately true equation for single slit diffraction, where theta is the angle through which it diffracts. The maximum value of sine theta is 1. For obvious reasons, the maximum amount of diffraction is 90 degrees here. So if 90 degrees is our maximum diffraction, sine theta becomes 1, and that's what you're left with, that lambda is equal to the slit width. Okay, moving on, tick the boxes to show which arrangement allow an interference pattern to be observed. So if we want to make an interference pattern, the important thing here is that the waves must be coherent. That's the phrase we use. They have to be coherent to form an interference pattern. And coherence implies roughly they're all the same wavelength or the same frequency, but better the same wavelength really is the key thing for us here. All the waves have got to be the same wavelength, and to produce an interference pattern we ideally need two sources that are coherent. So here we have two loudspeakers. They're both connected to the same signal generator, so they're both the same wavelength. There are two sources, so yes. A sodium lamp, this is a sodium bulb. It's a gas, it's a discharge tube. So, it works by electrons dropping between energy levels. Therefore, all the photons have the same energy. Therefore, they all have the same frequency. Therefore, they all have the same wavelength. Are there two sources? Well, there's just one, but since it diffracts from here, it passes through both of these slits and it behaves as if it were two sources that are coherent. So, yes, monochromatic, coherent. So, yes. Single microwave source, again, this will spread, it'll pass through the two gaps, and those will behave like two separate sources that have the same wavelength. Yes. Red laser, blue laser, they're different colors, therefore they're different frequencies, different wavelengths. No. So this next part of the question I thought was actually the interesting bit, so let's have a careful look at this. Laser light is shone at a diffraction grating with a slit separation of 2.4 micrometers. This is a diffraction grating, so this is very much the equation we want to use. Remember, diffraction gratings are very precisely engineered. 2.4 micrometers is pretty tiny. So we use a very exact equation for them. Also, diffraction gratings give us single pinpoints of light, not kind of spread out fringes. So we use the exact version of the equation when it's a diffraction grating, not the approximation. The approximation is only good for double slits and single slits. So this is the equation that's going to come to play here. 9 bright beams are produced. You always get an odd number of beams because the middle one always exists, and then you have symmetry. You've got, 2 on each side always. So if I write on the order n equals the n from this equation, it's called the order. This is the 0th order, n equals 0. That means there's no path difference here. The path difference is 0 times the wavelength. No path difference at all. Both beams, or all beams rather, have traveled the same distance to get here. This is n equals 1, n equals 2, n equals 3, n equals 4, and similarly on the other side, 1, 2, 3, 4. Determine the max and min possible wavelengths for this light. So we're given d, and we're looking for the maximum and minimum possible wavelengths that are going to produce 9 bright beams. The limit here, the limit to diffraction is 90 degrees. You can't diffract through more than 90 degrees. So if we think about the limit of diffraction and apply it to this, if I could change the wavelength, if I could vary lambda coming out of this laser, what happens as I increase and decrease lambda? As I increase this wavelength, all of these will spread further apart. Look at the equation. If lambda goes up where n and d stay the same, then sine theta increases. Sine theta is an increasing function in the range 0 degrees to 90 degrees. So therefore theta increases. So as I increase lambda, all of these would move in this direction. What's the limit then for me seeing 9? It would be when the n equals 4, the 4th order one is at 90 degrees. So that's my first limit. N equals 4 implies that theta equals 90 degrees. If I think about spreading the opposite way, as I decrease lambda, all of these fringes move in this direction. What's the absolute limit for me still only seeing 9 bright beams, not seeing 11? Well, that would be when the n equals 5 is at 90 degrees. The 5th order at 90 degrees. So those are the limits. That's any value of lambda that is in between these two conditions is going to be okay. So 90 degrees implies sine theta is just 1. So what I'm left with then is 4 lambda equals d. And d, given in the question, 2.4 micrometers, so 2.4 times 10 to the minus 6 meters. And 5 lambda equals d. 2.4 times 10 to the minus 6 meters. Yeah, I've just realized I don't have a calculator literally at all. Hold on, surely Malcolm, you can do this. That implies I can do this. 2.4 divided by 4, surely 0.6. So 6 times 10 to the minus 7. And 2.4 divided by 5. 4.8 times 10 to the minus 7. So those are my two limits. So my final answer then puts lambda anywhere between those two. Hopefully that makes sense. Again, just to reiterate, if you found this little video clip useful, this is very much a trial. Do let me know, and I'm happy to make more of them. Feel free to request specific questions from any past paper or specific topics, and I'll dig up a question. Thanks for watching.